So welcome to this training action on solutions for alternative water sources and a potential contribution to a more robust and climate-proof water system. This is a training action which will share insights on 3 demonstrations from Living Lab Flanders and also 1 tool. Before we get started, just some quick announcements. So we'll be recording this training action. Most of you already have your cameras off, so if you don't want to be on screen, then please keep your cameras off. Also keep yourself muted unless you would like to share or say something, and you can also use the chat functionality if you have any questions. And also we've been asked to share a survey to get sort of your evaluation on the training action. So I'll be circulating an online form which can be used at the end of the session to provide your input. Just really quickly, the agenda for today. So we'll have briefly an introduction to provide a bit of context. Then we'll have a presentation from the Watergroep and Aquafin on increasing source resilience for drinking water production. This will be followed by a presentation from Proefstation and Vito on urban stormwater reuse for agriculture. And then at the end of the training action, we have a bit of time for questions and a discussion. Just quickly, some context. So in Flanders, there's growing population within the region. There's variability in rainfall patterns and extreme events. There's also, which is pushing this growing need to bring about some sort of change within Flanders. And as such, the ambitions of Flanders is to mitigate impacts of the impacts on drinking water production, stormwater management, and water sustainable resource for agriculture. And part of the B-WaterSmart project, the vision in Flanders is to become more water smart through the application of alternative water resources, for example, water reuse, and improving water use efficiency. And so more specifically, we're looking at increasing the availability of water through demonstrations of water smart solutions, to valorize the technologies applied for larger scale application to other parts of the water system, and to assess their potential impact and contribution to more circular water systems in Flanders. With that in mind, the objectives of today's training action will be to provide insights into different options to improve water system robustness using alternative water sources, looking particularly at the requirements and key success factors, and also the potential to contribute to solving specific water challenges for the region. So as mentioned before, we'll have a series of presentations. And so our colleagues from the Living Lab Flanders, Living Lab are here to provide their insights based on the activities which they've been doing. So we'll start off with Peter from the Watergroep, and he'll be also accompanied later by Beerte from Aquafin. So could I invite you to turn on your camera, Peter, and then also Beerte after, and then I'll give you the floor.
Okay. Thank you also from my side. Welcome to this training session. First, Living Lab Flanders, there were 2 locations. One is that were dealt with. One is focusing on the drinking water supply in the region of the Blankaart, and the other part of the pilots were done related to the region of Mechelen. So what are the challenges for our water production center in the Blankaart, Wouwmen? We use in that region, it's the western region of Flanders, and the only water source we have available is surface water. We have at that location historical quite large reservoir, about 3 million cube of water we can store. And we have a very performant treatment train to produce our drinking water, going from nitrification, coagulation, sand filtration, and after the post treatment with ozone, activated carbon, and a disinfection. So that looks very good, but we have some problems with the water intake. So as we are dependent on the river IJzer, there are various parameters we have to control, and that are chlorides, pesticides, nitrates. Sometimes we have excess of water with floodings, and sometimes there is no water at all in the river Ezer. In some years, there are several months we cannot take in some fresh water, which brings our water supply under pressure. Next slide, please. So what are the options to make the system more resilient? Within B-WaterSmart, we investigated two different technologies or options. The first option is to run inline treatment by CCRO. So that would be slightly more. Okay. And the second option is to use the wastewater from the municipal wastewater plant, which located only 1 kilometer away from our water treatment plant. And after pre-treatment, that water would also be reused as source for drinking water. Next slide. So to evaluate both options, we did run two pilot studies. One was we selected the closed circuit reverse osmosis system. I will come up later on with more details about what that means. And the pilot had a capacity about 10 cubic meters per hour. And the water group was the lead partner, and our technology supplier was Waterloo. And the second pilot was run by Aquafin, and there we tested ultrafiltration, reverse osmosis, active carbon, and ultrafiltration, UV and disinfection as treatment step for the treated effluent with a capacity about 1 cubic meter per hour. Next slide. So did some visual of the pilot location. Next slide. So more details about the CCRO. So a CCRO, a closed circuit reverse osmosis, use exactly the same membranes, the reverse osmosis system, which are quite well known. What is different is the way of operation, whereas conventional reverse osmosis has always a stable operation and a continuous production of permeate and concentrate. With the CCRO, we are using a cyclic operation, where we first have a filling phase, the plug flow, and in that phase, we are filling the system at low pressure, and the concentrate is I start again. Sorry. So the first phase, the filling phase, the pressure pump is on. We are filling the system with fresh feed water, and there's almost no permeate coming out. Afterwards, at that phase, there's something wrong with the slide. The main difference between the CCRO and the reverse osmosis is that we have a circulation pump. So during the normal production phase, we are continuously recirculating the concentrates, which means that there's no concentrates coming out. There's production of permeates, and we are continuously filling the system with some fresh water. And this amount of fresh water is exactly the same as a permeate we are producing in that phase. At a certain moment, the production phase is finished. That is done when we reach a certain high pressure or certain time setting. At that moment, we start again with a filling phase. So the circulation pump is stopped, and we are discharging, opening this valve so that we have a concentrate flow, and we are With the fresh feed water, the concentrate is discharged from the system. What is the main advantage of this cyclic operation? As we have an additional step, so we have a circulation pump, which is not in place in conventional reverse osmosis, which means that we have a control over the cost flow over the membranes during the cycle. And that makes the system less sensitive for membrane fouling and membrane scaling. A second benefit is that we have a limited time that we operate at the highest pressure. So because at the beginning of the cycle, we are working at low pressure, and only at end, after a long time circulation of the concentrate, we reach the highest pressure that we need for the permeate generation. And that means that we also have one of the claims is that there's a lower energy usage. Another benefit is that with this CCRO system, as it is less sensitive for fouling, we can have a very high recovery, up to 95%. Next slide. So this is a visualization of the cyclic operation of the CCRO, where we have first the plug flow phase at low pressure, where we have the filling of the system. Afterwards, we start the production of permeates, and during the cycle, the pressure is going up until we reach a certain maximum pressure, and then we start over again. Okay, next slide. So these are some pictures of the internals of the pilot unit, where we have chemical injection points for anti-scalant and pH correction, the cartridge filter to protect the reverse osmosis, the low pressure pump, and the high pressure pumps, and the recycle pump, which is a new item in the design of the pilot. Okay, next slide. What did we test during the 6 months of piloting? So the main variation, we split up the pilot test in 5 different phases, and we started at a water recovery of 85%. If you know that the normal reverse osmosis works traditionally at 75 to 80% of water recovery, we already started high. And during the pilot, the different phases, we were able to increase the water recovery up to 95%. So only 5% of concentrate is produced. During the first 4 phases, we have the same flux over the membrane. And the final stage, we challenged the system and we went up to the maximum flux. Okay, next slide. What are the main results of the CCRO test? First, we are going to look at the main inorganic components, the salts. When we look at the bivalent salts, both cationic and anionic, they are completely removed by the CCRO system, which we expect with reverse osmosis system membranes. For the monovalent ions, we see that there are some ions are passing, and when we look at the final phase, phase 5, we see that the chloride retention is still 90%, which is sufficient for our drinking water application. Of course, when you go from 95% of water recovery up to 95%, more the permeate concentration of the chlorides and other monovalent ions is slightly increasing, but that's expected. Next slide. Okay, when we look at the retention of the micropollutants, we see that there are, we did analyze about 123 components in total. Of the micropollutants, mostly pesticides or pharmaceutical residues, There were about 46 detected in the concentrate. Of course, the concentrate is about 20% higher in concentration, 20 times higher in concentration compared to feed. So it's logical that we can detect more components in the concentrate than in the feed component. In the permeate, there were still 5 components detected. But all those components were below drinking water limits. So also for the retention of micropollutants, we had a positive evaluation of the C3O system, even at a very high water recovery of 95%. One remark is that as we could not evaluate the pilot the test during 1 year, there may be some bias because some of the pesticides are only detected in some seasons, so some additional work has to be done. Next slide. So the main conclusions for our C0 pilot. During the full test, we did not have any indication of membrane fouling. Even at the extreme water recovery of 95%, there were no indications. We did not do a final membrane autopsy because the chance that there would be anything visible was too low. So the operation was very stable. So we are fully convinced that the C0 may help to reduce issues with fouling, and we can reach the 95% water recovery. Related to the water quality, both for the main elements and for the micropollutants, the retention was okay. And the last conclusion related to the energy consumption, it's always difficult to translate energy consumption data from a pilot unit to a full-scale unit. But after evaluation, we did not find any, we could not confirm the claim that the C0 was really more energy efficient. So at this moment, we conclude that in our case, the energy consumption will be the same order of magnitude at a normal reverse osmosis system. Okay, and then we go over to the second case of Bertha.
Yes, thank you, Peter. We also tested the second potential solution to increase the robustness of the drinking water production in the Blankaart Production Center, and that is the reuse from the wastewater treatment plant in Walma, as Peter explained in the beginning. So on this map, you see visualized the situation on the site. So we have the wastewater treatment plant of Walmen in the top of the image, and that's situated about 1.5 kilometers from the water production center. You see the large buffer basin situated next to the water production center, and that is normally taking surface water from the River IJzer and from a pond nearby. So there are several options when you are going to couple the wastewater treatment plant, and that is, for example, we can put the water into the large buffer basin, or we could also put the water a bit further in the drinking water treatment train. So to start our test, we took what we called the minimum effluent polishing scenario. So the scenario that needed the least treatment from the effluent, and that is when putting the water at the very beginning of the drinking water treatment, and that is in the buffer basin. So the first thing we did, and now we can go to the next slide. The first thing we did is identifying the critical parameters for this minimum effluent polishing scenario. So these are the parameters that do not have a sufficiently low concentration to be added to the buffer basin. And for that, we look for example, to the intake requirements that the watergroep has for taking in water from the river IJzer. And they have these requirements for nutrients, nitrogen and phosphorus, for chlorides and conductivity, and for pesticides. And these parameters, they cannot meet the intake requirements. So they need polishing before we put them into the buffer basin. Then we have 3 other groups of contaminants from which there are no intake requirements available, but we suspect them to be, we suspect that they might be an issue for the further drinking water treatment, because their concentration is higher in the effluent than what can be expected in general in surface water. And it's for pharmaceutical compounds, for microbiological indicators such as bacteria, viruses, etc., and also for organic material. You see that the nutrients and the organic material are indicated in green. That is because these are not really a problem for the drinking water quality at the end, but mainly for the algae growth in the buffer basin. And the other parameters such as chlorides, pesticides, and pharmaceuticals and microbiology, they are mainly of concern because of meeting the drinking water limits. So what we're going to do is we're going to test a pre-treatment to polish the water before it can enter into the buffer basin. So we have put a small-scale pilot container at the wastewater treatment plant of Walmen, treating 1 cubic meter an hour, which was not effectively sent towards the water production center, but so we can see which quality can be reached and how these technologies would react to the secondary effluent from the wastewater treatment plant. So here you see a picture of the pilot container. And if we can go to the next slide, then there is a scheme. Yes, so the pilot container, as Peter already explained, contained an ultrafiltration membrane, a reverse osmosis membrane, and then optionally also a granular activated carbon filter and an ultraviolet disinfection unit. Next slide, please. So these are some pictures of how the pilot looked like from the inside. The first picture is more like an overview, and the second one you can see the ultrafiltration membrane. The third one shows the 2 reverse osmosis membranes that we had that were placed in series. And then the last picture on top is in blue the granular activated carbon filter, and then somewhere in the back there is a UV unit, but you cannot see it very well. And then at the bottom the chemical dosing unit for cleaning the membranes. Okay, let's go to the next slide. So the main question was concerning water quality. So is this treatment sufficient to achieve a good removal of these critical parameters that we identified in the beginning? And the answer is yes. You can see here, for example, the suspended solids. They are mainly removed by the ultrafilter because the difference between the concentrations in blue and the concentrations in bright green, there's the most removal. Then on the other hand, nitrate and chloride, then you see a big difference between the concentration in green and the concentration in pink, which means that there is the biggest removal by reverse osmosis. So this reverse osmosis was really needed because of the combination of salt removal and nitrate removal that was needed, so that it was the most optimal choice to go for reverse osmosis. And also phosphate is removed both by the ultrafilter and by the reverse osmosis unit. Concerning micropollutants, let's go to the next slide. We tested their removal efficiency both over the reverse osmosis membrane and over the activated carbon filter as a single treatment, so without a preceding RO. And then you can see that in pink, the removal rate over the RO membrane is in generally a lot higher than the removal over activated carbon without a preceding RO. So this RO can really help to reduce the risks related to micropollutants such as pharmaceuticals. So next slide, please. So for water quality, the answer is yes. We can reach the sufficient quality to put the water into the buffer basin of the water production center in the Blankaart. And we even think that it does not have to be only in the buffer basin. So the quality that we reach after the reverse osmosis is quite a good quality. So maybe it can even be put after the somewhere else in the drinking water treatment train, for example, after the pre-treatment. Before that, to be sure, we need a quantitative risk assessment, both for microbiology and for chemicals, to give us additional information on whether this extra polishing with granular activated carbon or ultraviolet disinfection is really needed, and whether there are enough safety barriers when putting it into the drinking water train at the later stage. Okay, but then this quality is not the only thing that you have to look at when you want to do such a direct reuse scheme. There's also for quality, there is a connection with the revision of the Urban Wastewater Treatment Directive. So for now, we started from the secondary effluent of the wastewater treatment plant in Waume. But due to the revision of the Urban Wastewater Treatment Directive, some wastewater treatment plants all over Europe will be equipped with a tertiary or even a quaternary treatment step for further removal of nutrients and or micropollutants. So that will give you another image to start with, and then maybe you can reach the quality with less advanced technologies, but that's unsure for the moment. Next slide, please. And then, as I said, the quality is not the only thing to look at. So we also experienced some operational issues, which we had to investigate further. And these operational issues, they were situated mainly at the pre-filtration and at the ultrafiltration, as indicated in green. And on the next slide, you can see some pictures from this pre-filtration. It was a small grid of 100 micrometers. And you can see on the graphs in purple, there is a pressure drop over the pre-filtration. And then in red, you can see the pressure drop over the ultrafiltration membrane. So the figure on top shows that we had some periods with an uncontrollable pressure increase over this pre-filter that we could not reduce through its self-cleaning procedure. And then the graph on the bottom shows that we have in other periods, we had a stable pressure drop over the pre-filtration in purple, but in these periods, we had an uncontrollable rise of the pressure drop over the ultrafiltration membrane. So there was really a lot of fouling. And when going to the next slide, you see an overview of the challenges that we had. This fouling was related, for example, due to the fluctuating effluent quality and its susceptibility to the weather conditions. So the amount of nutrients in the water and the amount of suspended solids, they really depended on the weather conditions, and so the flow rate within the wastewater treatment plant. Also, there was some dosage of polyelectrolyte in the treatment train in the wastewater treatment plant at this rainy weather conditions to improve the settling in the treatment plant. But this polyelectrolyte induced also some irreversible fouling in the membrane. There was also a high potential for biofouling in the water, so still some organic material, still a lot of nutrients present, inducing a lot of tripods and other biofouling in the ultrafiltration membrane and in the pre-filter. And it took us some time to define the proper conditions for the self-cleaning of the pre-filter and the backwash of the ultrafiltration membrane. To get a good operational a plan to do this cleaning. So what we propose to do in future designs and future operation is, for the design, we have two recommendations. The first thing is to add a pre-disinfection step to quench the main biological activity and reduce biofouling, and also use a multi-stage pre-filtration for removing the remaining suspended solids so that it is less prone to clogging. For the operation, we have some other recommendations that is aiming for continuous operations, so avoiding standstills because during standstills the installation is prone to biofouling. Also evaluate your design and operational functionalities of the wastewater treatment plant, the secondary wastewater treatment plant on its own, especially the polyelectrolyte dosing, because this can induce a lot of problems in your post treatment. Do not allow the pressure drop over the membranes and the pre-filter to rise too high, because this will induce irreversible fouling. And have a look at the chemical cleaning, the self-cleaning, and the backwash, how often you perform them, do them rather more regular than more late, because it's very important to keep your membrane clean. Okay, so let's go to the next slide. Some slides issues to take into account when thinking about reusing effluent for drinking water treatment is also the impact on a receiving water body. So you're taking the effluent away from the water body where it was discharged at first, and this can impact the aquatic ecology on this place, also the salinization and the navigability for ships. So that's something to discuss with the owner of the watercourse. You were using membranes, so of course the concentrate is an issue that was not looked at in the B-WaterSmart project, but is something that will be taken into account in future projects. There might be some concurrential for effluent reuse, so there might be multiple potential end users. So you need a framework which we made in Flanders based on the input from the community of practice. So you need a framework to decide who can use the effluent for every wastewater treatment plant. And of course, for the drinking water itself, effluent reuse is only one of multiple integrated solutions. So there are many solutions possible. Today we discussed only two of them. The first one was upgrading the treatment train with CCRO. The second one was reusing effluent, but of course these are only two solutions, and there are many more solutions possible. So it's always a trade-off, both in cost and robustness, but also in sustainability. And the main goal in this is to limit the groundwater reuse and protect the natural water sources, but also do source diversification to create this robustness. Okay, and then next slide. So to conclude this drinking water case, we can conclude that in the region of Waalmen in Flanders, the regional water supply can be improved by the two solutions that were tested. Both alternatives reduce the risk on low water quantities during drought, and they increase the water quality and therefore the robustness of the treatment. There are still some remaining challenges for both solutions. So we have concentrate streams in both. Mainly for effluent reuse, we have some operational issues left, and we have to evaluate the impact on the receiving water body and on the environment a little bit closer. But these solutions will be evaluated in the future together with other regional options. And we will also look at this through a more integrated approach, but that was part of another tool developed within B-WaterSmart, a regional analysis, which is covered in another training action. So that was it for the drinking water case. We can now go to Sander.
Yes, thank you very much. Then yeah, we'll move on to a slightly different topic, but still on trying to improve the robustness of the water system within Flanders. So I'll give the floor to Sander and later to Free to say something about the urban stormwater reuse for agriculture. Sander.
Yes, I'll try to get the all right. You are clicking the slides. All right.
Yes. Yeah.
So hi, I'm Sander from the proefstation voor groenteteelt. I'm going to talk about the stormwater reuse for sub-irrigation. Now, first I'm going to give a little bit of a situation sketch. Then I'm going to talk about the buffer basin itself, which important parts we had to adapt at the design and the construction of the basin. And also the control tool to manage the level of the basin itself, which is quite important to succeed in the reuse of this water. Then about the sub-irrigation system, a little word, and then Free is taking over to really go in depth on the control tool of the sub-irrigation management and how to reuse the stormwater in the sub-irrigation part, how that is managed. And then some conclusions, so you can go for the next slide. So a little situation sketch, as you can see on the map. In Flanders, we have a very nice urban planning system, which is we don't. And that means if you have a village, like on the right side, this is Hombeek. It's next to the city of Mechelen, between Antwerp and Brussels, to put it in a bigger scale. Next to it, you have buildings which are built at the roads in between villages, which means that you have a lot of paved area, roof surfaces, a little bit more, in the countryside, let's say. When there are heavy rain events, all the precipitation on this paved area is flowing into the river system faster than it would in normal conditions, which then gives more risk of flooding downstream, which is the case in Hombeek, so the small village. Now, normally, the normal solution is to build a retention pond. You can see where it was going to be built, or it is built, but now an adapted version of a normal one is built at the red dot in the middle of the map. And as you can see on the map, there is a lot of agriculture area around this red dot. So the problem we also have in Flanders, not only risk of flooding because of this pavement and a water system that is contributing to discharge as fast as possible, but also we have had some very dry years. Now, not this year, but previous years were quite dry. We had dry summers with a lot of problems. And then we see that we have a lower groundwater table, we have dry soils, there is less water infiltrating in the soil. So we sat together around the table with a few partners and said, well, they're going to build a buffer basin there. Why can't we use it in a nice way, this water? And why can't we use it to sub-irrigate the agricultural area around it and sort of using the existing drainage systems in this agricultural area to not only drain when it's needed in winter, it's still needed, but also in summer when it's dry, use the water in this buffer basin, which we will then try to store, use it to sub-irrigate via this drainage system. So that's what we are doing there. So you can go to the next slide. And now this is being built, minus the arrows. I drew them on top myself, but you can see, you can follow the water if you follow the arrows. So in the left corner, you see a lot of houses. This is a real picture from the buffer basins. And those houses, their roof surface is connected to a stormwater draining system. And from the street on, it goes if you follow the blue arrow, it goes into the stormwater basin. And this stormwater basin is only used to store or to receive clean stormwater. There is another arrow, the yellow arrow, that goes to the other water basin. This is mixed water, so there is a chance that there will be an overspill of some sewer, which we don't want into our clean water basin, and that is then buffered in the other water basin. This is a normal working buffering basin, and this other water basin, it just discharges in the creek, which is lying at the left side of it, as it was before there were any buffering basins. So then all the water just came into the creek, so the stormwater and the overspill of the sewer. Now, the stormwater basin itself, if it's full and it needs to discharge, it can discharge in the buffering basin beside. But also we can pump water from it, put it through a water treatment. It's just a double security measure. And then it goes to the fields for sub-irrigation. Then you can go to the next slide. So we'll start with the beginning. This is one major and important adaptation we had to do, and that is a separation. So I already put some emphasis on it. It is really, you can see the two pipes coming out of the street. This was really important that we really keep the clean water separated from the potentially slightly polluted water, because we don't want to use it, we can't use it legally, and we really don't want to use this water. So we physically separated it from the source on, so it really doesn't mix, which was quite important to do. That's why it is not one buffer basin, but we actually have two of them. All right, you can go to the next slide. Then another important thing, so the clean water basin and the stormwater basin, we lined the sides with HDPE plastic foil. And why? Because a normal buffer basin allows infiltration locally. And we want to infiltrate, but we want to infiltrate not out the side of the basin. We want to infiltrate a little bit further where the fields are, where the crops are growing. So we want to really minimize the infiltration possible, and that's why the sides were lined with this plastic foil, as you can see in the picture. You can click another time, Raoul. Thank you. But we, at this site, we had some boundary conditions which made that we have to have an open bottom. This seems very contradictory, because we want to store the water, we really want a watertight basin, but because of the railway lying next to our basin, we couldn't dig any deeper to get enough pressure of soil on top of the bottom if it was going to be sealed, to get enough volume, because then we had to dig too deep, which meant that the railway next to it would might become unstable. To make a long story very short, we have to have an open bottom basin, which is not ideal. And to say if we want to use this concept of basin or of double use for reuse of the water, you really want to make your basin watertight if possible, and if not, you make it as watertight as you can. So we reduced the surface of infiltration with this plastic foil, and that helps already. All right, you can go to the next slide. Then maybe the most important part of all, this is the weather controlled valve. As you can see in the picture, This is just a valve, you would think, but it is smartly managed by some software, by a software tool developed by Aquafin. And this valve is, as it says, weather controlled, and this is really the key to save the water in the basin. This is it. Yeah, you can go to the next slide. So the working of a normal buffering basin, as you can see in the picture, is just you have the entrance at the left side, and then at the right side you can see in the dike there is a small opening. When water is rising, water can be buffered into this basin. Then if the creek level, so at the complete right, if it is low enough, then water will flow out of the basin. This is how, all of the basins except of ours now work in Belgium and around across the globe a little bit. I just go back, sorry. All right. And so this is now how it works. And it really empties as soon as it can. So if you look at the graph, most of the time this basin would be filled. This is modeled on our basin, this graph. It would be filled around 10% or empty, and it barely gets around 50% of filling, and that's in really, really bad weather conditions. Now we adapted our basin with this weather controlled valve, and then you can go to the next slide, and then we get a total different situation, because now we keep the valve as close as possible because we use a weather forecast. Now you can say weather forecasts, they are not as accurate. We only use a weather forecast going 6 hours in advance, because else it would be too unpredictable. And by using this weather forecast, we can calculate on the surface that is attached to the basin how much water is coming in. So let's say 200 cubes of rainwater will be coming into the basin. Then because we know the volume of the basin, we know the level of filling, the filling degree of the basin, we can calculate like, we have enough space, so we don't have to open the valve. The software automatically calculates this. The software also says like, we have to open up a little bit, let out like 100 cubes of water, because we need the space to store the new water in advance. If we then model it to our basin, you can see on the graph that around 50% of the time we have an almost filled basin, which is nice because that is the water that we can reuse instead of dumping it into the rivers and let it flow to the sea. We really keep it locally. We really guard it. All right, you can go to the next slide. So this valve is really the key ingredient of our concept of storing the water so we can reuse it, because without it we could not. Then you can go to the next slide. Now another adaptation in a normal buffer basin, it works all gravitarily. There is no pumping or stuff going on. But yeah, we store the water, but we also have to have some infrastructure to pump out the water out of the basin. And that's what you can see on this picture. So in the opposite corner of the valve, there is a deeper pit installed. Why is this? Because you want to pump water. We really want to use all of the water stored in the basin. So your intake point has to be a little bit lower than the floor. If it is not, then you have a dead zone with water you can't use. Now it's not, the intake is not at the bottom of this concrete pit. It is the bottom of this pit is a little bit lower because you can have some sludge or sediment which then settles at the bottom of the pit and not where your pump is pumping the water out. And then above, as you can see in the bigger picture with the red circle, you see a container. This is a water treatment And also our pumping station is there. So you can go to the next slide, please. Thank you. So yeah, the container you can see here on the pictures, it is actually a very simple thing. We can do some chemicals. There is a sand filter. There are some tapping points to measure the water quality. That's basically it. There is some room to install a carbon, active carbon, but it is not installed yet. And this is just a double safety. Yeah? So we really want to be safe with starting using the water, because yeah, it's new. It's something we didn't do beforehand. So we really wanted to be safe. Now, after passing all this, we really can just start reusing the water, and then we go to the sub-irrigation system, because there also we sort of build out of the box. We took a drainage system and we actually are using it the other way around. We are using it to just get water into the ground, not water out of the ground. So you can go to the next slide. Here you have a scheme of our sub-irrigation system. So at the right you have the buffering pond and the pump. Also the water treatment is there. And at the left side you have the field. In those agricultural fields, there is drainage around 1 meter below the surface. Now the drainage pipes, they all are running to a collecting drain. So there is a collecting pipe, and at the exhaust of that pipe, we have installed a remote controlled level control. And so you can see it as a bathtub. Where normally you have where you put the plug. If you put a tube and then a plug a little bit higher, the water has to rise until it flows over this unhindered drain, this unhindered overflow. If you lower the overflow at the drain level, then your drainage works as normal. If you rise it, then it keeps the groundwater and it stops the draining, and it even gives you room to infiltrate the water. You can pump water into the field and it won't flow to the ditch, but it stays more into the field. As you can see on the picture now, next to the water course, to the right of the water course, you can see that the water has to rise a little bit more before it flows over and can go to the water course. Some other important thing we added to the drainage system here to easy up the sub-irrigation is an air vent at the other side, because you don't want any air trapped in your drainage pipes, because it blocks it can really block the water flowing around. So by adding also air vents at the other side, you get a more reactive system, which makes infiltration but also drainage a little bit more easy. And we really want to maximize, or being able to maximize, this infiltration. Now, how this is controlled, the tool to control this together with the water in the buffering basin, that is my colleague Free, who is going to talk about this. So Free, the floor is yours. No, sorry, one more slide. A little bit on the performance. So the basin, it is now fully operation since February, and we don't have any uncontrolled overflow so far. It has been a very wet season, so a lot of water has come into the basin. Now, because it was so wet, the agricultural area didn't have any need for excess water, but potentially we could have used already 25,000 cubes of water. That is a lot more than we thought we would have. So if you ask, is the basin working? Yes, it is, and very well. And now Free is free to go.
Thank you, Sander. So I will take you a little bit through the sub-irrigation control. So yeah, if all this water is available in the buffer basin, we're not going to send it just straight away into the fields. We're going to do this in a more smart way, and to do this in a more smart way, we made this decision tree schema that you see there, and I will take you through it, or at least not in detail, but through what we took into account in this scheme. Next to giving you an idea of what was taken into account, I also added some yellow symbols. Yeah, Rul, you can go to the next slide. Thank you. Like you see here in the scheme there, and that's to indicate where we need a measurement from the field. So that is where we need some sensor data that was installed on the field. So the first thing we take into account is, of course, weather. Next to precipitation, we also take temperature into account, purely for avoiding damages due to freezing. So when it's been too cold for a long time, we shut the system down, and we also send an alarm to someone so they have an idea, it's been cold for a long time, maybe it's a good idea to go check. Then something else we take into account is the amount of fields that is available. Next slide, please. So the system is fully automated and controlled from a distance, but very important thing is that the farmer still has everything in their own hands. So at any point they can say, we don't want any water in my in his or her field anymore. So we can shut the water supply to the field off. It can either be that the farmer says, I don't want it for the next 2 weeks because I'm planting some crop on it, or it can they can say, I don't want my field to be involved in the next year, for example. Then the next thing we take into account on the next slide is the crop that's on the field. So before I go into a little bit more detail on that, first, the sub-irrigation has two broad, let's say, statuses. One is when water needs to be evacuated. So because we keep the buffer pond as much filled as possible, that also implies that if rain is coming, first we need to let some water out to make room for the water that will come in. And then the water, in that case, the water needs to be evacuated. And the other status is that we want to make use of the water that is there for as long as possible. To do so, we take into account the crop that is in place. So if the water need is fulfilled for the crop, then we don't send any water to it. And if there's a water need, we will only send it in limited amounts to it, so it can profit ideally from it. And then the last thing we keep into account is when it does need to evacuate it, we do take into account the amount of water that is actually possible to evacuate in 6 hours, and also that we don't exceed the groundwater level, that the maximum groundwater level that can be in the field, which is also a boundary condition that comes from the farmers. Okay, then next slide, please. Okay, so as you can see, there were quite some yellow symbols there that indicated the sensor, and it of course also needs to be that means that equipment needs to be installed on the field itself to be able to control the sub-irrigation. So we have quite some sensoring. For example, you see there a level sensor. We have, if I'm not mistaken, 4 on the field. Then a weather station is installed there. Of course, these sensors, the data has to be ingested in some kind of data system. Therefore, we have some communication equipment on the field. We use LoRa and narrowband IoT. And then, of course, there are some things we need to control. So, for example, the valve in the drainage to manage the groundwater level. Okay, so all this has to talk with each other. So the sensors, what we need to control, and the steering algorithm. And there, to show how we do that a little bit, there is here a high-level IT architecture scheme to show you what components we need to make it all work. So on the left in green, you can see the data gathering. So yeah, we need to gather all the data from all the different types of sensors, and also the we have a connection to the buffer basin. Yeah, because that communicates how much water needs to be evacuated to us, and also if there is water in the basin in very dry periods, for example, that's also relevant. So that data goes into the database. Then we do some dashboarding on it, so we visualize the data that is coming in. That way users can see if everything is going right, if the controls are doing what is expected of them, whether the sensor is down, stuff like that. Or whether, yeah, if the system goes in alarm, you can check why it's going in alarm, for example. And then on the right in the blue, of course, we have our algorithm itself that calculates the controls. So it's triggered each 15 minutes and it couples back towards the devices on the terrain. Maybe they do need to change something, and also to the control system of the basin. But this is, of course, only the IT background, a little bit of the SIP irrigation itself. It, as already indicated a little bit, is also connected to the IT infrastructure used to steer the buffer basin. Yeah, this is just very short. They have the IT architecture behind it is, of course, also more broad than is indicated here, but just I wanted to show you how that the connection was there, so that they process also some of the data that we gather, and but also mainly take into account the rainfall forecast, like Sander already explained. Okay, so that's for the IT architecture. Just, yeah, we want to show this to give you an idea that this is also quite an important aspect of the whole SIP irrigation part that you cannot underestimate if you start something that is quite similar. And then to conclude, we still have some lessons learned that we would like to share with you. So first of all, we already saw that the proactive control of the buffer basin performs very well, that it retains quite some water, and it's hence advantageous to reactive control. All right, and that we also saw that the amount of water we could potentially reuse is way more than was actually modeled. Of course, we were not able to use it yet because it's been raining so much lately, the past months. Then as far as the SIP irrigation system goes, we already saw that the drainage can be successfully used as SIP irrigation, and it can not only help with irrigation through the capillary rise for the crops, but we can also use it for groundwater recharge and keeping the water in the system as long as possible. And then finally, maybe the most important thing, we do really believe that replication is viable. However, each project has its own situation and its own design. Hence, it needs to be tailored a little bit every time, but the concept is replicable, and we build it in a way that we have some modular building blocks. And I do believe that in another situation, each of these building blocks can be used in some way, so you don't have to start from zero. Okay, I think this was everything we wanted to share from the Mechelen case.
Great, thank you very much, Sander and Flee, for that explanation on the stormwater reuse approach in Flanders. At this point, yeah, we'd like to open the floor for questions or discussions. So if you have any questions, please feel free to raise your hand or put it in the chat, or you can turn your cameras on. I see that Peter, you put your hand up very quickly, but you put it down, so I'm not sure if you...
No, it was wrong click.
Yes, and I would also like to invite the speakers to turn your cameras on, then the others can see all of you who also spoke. But if there are no questions for the moment, maybe I have one for Peter. In your presentation, you mentioned that you have a recovery of 95% and the remaining 5% of concentrate. What actually happens to the remaining 5% of the concentrate? Is that, where does that go, or are there regulations around what can be done with it?
That will be part of a follow-up project that we are doing together with the University of Ghent. On the one side, the 95% recovery is very useful because we need all the water that we have available in the reservoir to produce drinking water. So that's the reason that the 95% is that important. The 5%, the residual 5%, maybe we can discharge, but there will be some requirements, discharge limits. We already did some investigations, and for this specific case, mainly the nutrients will be an issue, which means that we are looking now at nature-based solutions to remove the remaining nutrients. And for the micropollutants, which may also be an issue, the additional quaternary treatment that Aquafin has to do may be an opportunity that also those concentrations will be lower in the concentrate, but work to be done further.
Yes, perfect. Thank you. And I see in the meantime, Julia has raised her hand, so please feel free to ask your question.
Yeah, hi everyone. So first of all, thank you for all this information. And I have a question to the case in Mechelen, the buffer basin. So Sander, you said that the water treatment is working, and you could have saved 25,000 cubic meters of rainwater. So now you have purified this water. Do you have any other use of it? So where is the water going if it's not needed for the irrigation?
Now, for the moment, it is going. It is overflowing, but controlled, so as intended, into the smaller buffer basin, and then it's just being buffered for the water system. It is because we set up our case specifically on the reuse for agriculture that we can't use this water at the moment, because our soils are really just full of water for the moment. Some crops are like 2 months too late on the field, because farmers can't go on the field because it's such a wet condition at the moment. So in our case, this 25,000 cubic meters of water, it was buffered, but it is controlled, released into the water system again, as was intended. Now, you can imagine if you have another, you can use this concept and put other users on it. So if you would have like a factory which needed some water source or something, it's all taken in by this end user. Now, it's just because we use it for sub-irrigation and infiltration in agriculture area. Also to we see that it benefits the crops. We saw it in earlier experiments, but also it benefits the groundwater discharge, and rain that is falling locally, which was then discharged, is now infiltrating locally, except for the moment it is not, because there's too much water. But take away that boundary condition, we have a very special year this year, so I do not take this year for granted, and as a normal situation, this is really exceptional situation. Normally, you would have said, like we have the driest months in April, May, so we have a use for that water. We can then, when the farmers are off the fields, half of April, end of April, we can infiltrate it en masse. We can massively infiltrate this water. So it's really depending on the end user. If we would have had any other end user, or let's say flush toilets of citizens, if it's really in the city, I can imagine you can do a lot of other things. You can really use up this 25,000 cubes of water. So that's a long answer to a short question.
No, and it wasn't meant so critically. It was more a question of interest. We have the same situation here in Germany. We had also very wet spring, and it keeps on raining, and the fields are very soaked with rainwater. So we have this we are also thinking about working with buffer basins, but right now we would have the same situation. So I can imagine how your fields look like right now. But it's a pity to have all this nice cleared water now, and yeah, maybe there's also an alternative solution to use it for the houses right next to it. But of course, then you have already the constructed infrastructure, and then you need to transform that, and that's of course taking a lot of effort. So I can.
Yeah. And then you get, when it's not such a wet year and you can use it in the agriculture, we actually have more available fields than we have water for, because that's also a challenge. A challenge. Something we see is that we have only a storage basin of 1400 cubes. If building conditions had been else, so the railway wasn't there and stuff, it might have been a larger buffering basin, so we have more storage volume. But yeah, now we have a relatively small storage basin, let's say, for a lot of area.
Yeah, so in a normal spring situation, you would have had a bigger need of irrigation than water storage capacity.
Yes, yes. And yeah, certainly if you look then to the summers we have had the past 7 years, we had 5 very dry periods in those summers, and 2 with a quite wet summer. But it's for the dry ones, with the dry periods, we want to have this water stored. So we want to have a maximal groundwater groundwater level to start with. And if you then start with a high groundwater level, you have some capillary rise from that for your crops. Then you get into the dry period. You can sub-irrigate very gently to really keep up the moisture in the soil.
Yeah, very interesting. Thank you.
Great, thank you. Are there any other questions from participants? I see no raised hands. Maybe another question on the stormwater topic. Of course, creating a buffer basin requires a lot of space, so it requires land. In the case in Homebake, who owned the land before? How is that arranged?
I think it was some semi-public organization that owned the land. I do not know. Was it the Kerkfabriek? Yeah. So it was semi. Yeah, I'd say it was not the government, but the churches. Yeah, the Catholic Church actually owned the small parcel. It was once used for vegetable growth, but it's like a small parcel. Not so interesting. Then a youth movement was on there, so it was actually a not so used piece of agricultural area. And then the city of Mechelen bought the land to build this basin on. And yes, it is a space intensive operation, but you have to take into account if every farmer there has to build a basin to provide them with irrigation water, it all takes up a little bit of land. So why not combine this with a buffering pond that is going to be built? It was going to be built, this buffering pond.
Yep.
And that was an ideal place, so that's why Mechelen bought it there. And now we are actually adding a function to this infrastructure, and we also want to roll out this concept to existing infrastructure. It is possible, I think. We believe there are a lot of buffer basins all over Flanders. Some are quite small, maybe. Others are bigger. Why not start to also store the water and use it if it's possible? If there is, if there are end users for it, if it can be used in a good way. Or even if society benefits. It's also because that's the case actually here also. It's not the most efficient way of irrigating that we do now, so it's partly for society we do this. Also recharging the groundwater in let's say autumn when there are no crops growing. That's more whole of society that benefits then. So, but we really want this concept to be implemented on other buffer basins.
Yeah, great, thank you. I see there are still no additional questions. Maybe I can invite the other speakers, so Peter, if we, Birte, maybe Sander as well, if you have any final remarks that you'd like to share. So if somebody's looking to implement one of these solutions that have been presented, is there some sort of key takeaway message or key remark that you would like them to go home with? In the meantime, I see a hand has been raised. Maybe we can take the question first and then get your final remarks at the end. So maybe Noemi, if you would like to share your question or your comment.
Yes, hi. My question is, so how long does the water stay in the basin before it gets discharged to the crops?
Well, that depends. If we are looking into to a drier period, but there is no water needed in the fields, as Fries said, then the system will not start pumping. But if there is a crop in water need, it hasn't rained enough, and groundwater levels are dropping a little bit, then then we will start pumping the water a little bit. Because we just want to have, in the case of a drought, we want to be sparse with our water. We want to use it sparsely. We want to use it economically. We want to really have this capillary rise to the roots of our plants, instead of all the water just flowing to the groundwater. We have seen that groundwater levels can, in a severe drought, drop 3 meters below surface, so that's quite deep. There's no way plant roots will reach that of crops. But yeah, in case if it needs to be evacuated because there is a rainstorm coming, then we will pump it maximum capacity into the fields as we can. So to be short, it depends. If it's
Because
dry period, yeah.
I was thinking about the evaporation effect, like if you store it and you don't discharge it to the crops because you don't need the crops to be watered, you are losing it via evapotranspiration, like
Exactly.
But so it's like it's hard to store water.
Yeah. And we actually, I'm going to be honest, we also have to take into account the open bottom. So it's not watertight at the bottom. So if water levels are dropping really low in the region, then we have to take into account that even if we want to store it for 2 months, we will have some severe water losses due to evaporation and infiltration locally. Now, the local infiltration is not as bad because that's also the point of the sub-irrigation a little bit. But yeah, we have to fiddle a little bit with the with the software, with the parameters, so we don't store it so long that we lose actually more water than when we put it into the fields. But that's still something we have to fiddle around a little bit.
Yeah, ideally now we have a couple of dry months to experiment a little bit with it, to optimize it, because that's indeed a valid concern.
Thanks.
Okay, thank you. Maybe just before going to the final remarks, just a quick reminder, I put in the chat the link to the evaluation survey. So we'd appreciate, especially the participants, to fill this in, because it will provide valuable insights on how we can improve on future training actions like this one. And yeah, with that, then maybe I can invite Peter, if you have some final remarks, then Birte, and then we can go to Sander and then Flee.
Okay, so I work for a drinking water company, a utility company, so it's not promoting the CCRO as such. There are other parties that are doing the commercialization. I think that CCRO has certainly some added value related to very high water recovery, and also the fouling, the reduced fouling issues and scaling issues are a big advantage of CCRO. On the other side, there are also some additional costs. In general, they say that's about 10 to 15% higher investment cost. So you also have to think for your specific case, what is the added value of a C0 compared to a conventional reverse osmosis system? And a second final thought is that in Flanders we have some severe water scarcity issues, which are very specific for each region. And we need a combination of technology. There will be not one solution that will fit for all our drinking water locations. And for the case of the Blankaert, the combination of effluent reuse and C0, making the treatment system more robust, will help to overcome long drought periods. Okay, then I go further to Birte.
I think I would like to add as a final remark that there is a lot of potential with wastewater effluent to reuse it, not only for drinking water, but also other applications, and that it really depends from case to case what's the best application. But that it also cannot be taken for granted that you can just do reuse like that. There are other factors that has to be taken into account, like your impact on the environment and on the receiving water body, and also that the conventional treatment methods, which are really on the highest technology readiness level, so they are already applied on other water sources, that they cannot always as such be applied on wastewater effluent, because that brings in some complexity because of the water matrix.
Thank you. And then to the other case, Sander and then Flee.
Yeah, a little bit like Peter already said. It's the solution that we have here for or the thing we are providing here. It's part of a puzzle. It's not the solution which is going to get rid of all the problems. We are water scarce. We have to add a little bit of everything into the mix. But I think, yeah, using or reusing or other using existing infrastructure or would be existing infrastructure that's going to being built with a lot of extra functions. I think it's something we have to do. A certain to our water system, especially in Flanders, we have a very little space available. Everybody is competing for the last few square meters. But I think that those kind of solutions really add to the mix to become a water smart society, let's say. Yeah.
Thank you. Then Free.
Yeah, as a final remark, maybe that, yeah, so like reusing water on top of a buffer basin, for example, when you need a lot of parameters to take into account. That's not only going to be in sub-irrigation, but in any other situation, or most situations I can think of, you will need quite some sensoring, quite some sophisticated control systems. And from what we encountered, I would recommend to start with the IT scheme, or thinking about how you're going to implement all different data flows, etc., from the beginning on, so you don't bump later into things like, we have to do a lot of work into it because we didn't think of starting from it. Yeah, I would like to add that as a little takeaway.
Okay, thank you very much. Then I think we can close this training action. I'd like to thank Peter, Birte, Sander, and Flee for their presentations, and also to the participants for joining today. And I hope that you've learned something quite useful from this training action. So thank you, and enjoy the rest of your day. Take care.